Hello. Yeah. Good morning. Let's get started. We have a long day today also, and I hope all of you had a good banquet yesterday night, right? Um, so, um, so what I'll try to do, just let's quickly start with an overview of the today's program. I'll skip this. So as you can see, we did a little bit of change to the schedule. Filippo unfortunately could not present this his morning talk. So I'll introduce this NSF AI Institute ICICLE. I mentioned about that yesterday. We'll go into a little bit more details, and after that we'll have Doug Fuller from Cornelis Network presenting on the introduction to Cornelis Network and the Omnipath architecture. Then we'll have Martin from Dell presenting HPC platform efficiency for large-scale workloads. Christopher from University of Cambridge will be presenting MVAPIS as the Cambridge Open Datascale Lab. And after the coffee break, we'll have Stan and Alan from University of Tennessee will be presenting FFT computation towards Exascale. Then Greg Baker from Livermore having solving API integration problem with SPAC. Then we'll have Sajeev, Samir, and Prathmesh from NERSC trying to share their experience on MVAPIS2 at NERSC. And then we'll have the keynote talk will be given by Dan Strangioni from TAC. Typically, we put the keynote talk in the morning, but he's actually going through NSF review of his project. So it will get done by 12 o'clock, so then his time. So then we put it after the after lunch. And then Dong Lai from XScale Solution will be talking about accelerating HPC and DL application with MVAPIS2 DPU library. Then Amir will be talking about this MPI for Spark. This is the project we introduced, how you can bring all the big data stack and Spark over MPI. And then we'll be having a set of short talks, and then we'll finish. So that's how the program today looks like. So once again, we'd like to thank all our sponsors. So with this, let me start with the presentation. Let's see. Yeah. So just to give you background, I think some of you who attended MUG last year, we presented a very short overview because that time we just got funded on this. So this is one of the, from the US National Science Foundation, they have been funding very dedicated projects to really accelerate AI activities. So this is one of the 8 got funded last year. It is called Intelligent Cyber Infrastructure with Computational Learning in the Environment. The acronym is ICICLE. It is a $20 million for 5 years, $4 million each. There's a very large team I'll gradually introduce, and some of you sitting here are actually participating in that activity also. So if you take a look at look at some examples, like I know we are here totally talking about HPC, the computation, but the landscape has changed. Like earlier, if you remember, like in the HPC, you have some set of data, you load it to the file system and then start operating, okay? Where the data comes, okay? So that is the kind of a new domain where things are happening. For example, let's say you take a look at the agriculture, okay? So traditionally, I mean, people have been, the farmers, let's say they want to spray pesticides. So they have some knowledge, yeah, at this time of the year, they detect that, yeah, this kind of disease has happened, so they take a tractor and then spray it, okay? There is not much intelligence there. They're doing it in an ad hoc manner. But the idea is that if you have a really large field, might be you don't need to spray pesticides to the entire field. If you can identify that only some portion of the field is actually diseased, then you want to spray in that particular area, not the entire thing. Okay, so like this, let's say you want to harvest. You want to know the market condition. Should I harvest today versus tomorrow? Do I have the transportation logistic available? What is the market when I should be able to sell and make profits. So that means you need a lot of data, and these data are also coming from all different places. And you need to instantly take some decision. Instantly in the sense within 5 minutes, 10 minutes, you need to take decision, okay? So this kind of like think of like a urgent computing. Some of people have started talking also. So a lot of these new paradigms are coming, and then the question is how we adjust to that. So if you take a look at the left-hand side, so this is what I think most of us are familiar with. HPC systems, big data, machine learning, deep learning. Data is there in the HPC system, and we use this. But now on the right-hand side, if you see, this is the new computing continuum. So that means the data might be coming from the on-field sensors, like the digital agriculture I indicated. Might be a lot of sensors are out there in the field, and they are giving you continuous data, like how much water moisture level is there. Should this part of the field be irrigated with more water or not? So then the question is, how do you take that data and then compute either at the edge or the near edge or on the cloud? And if needed also, you can take it to the HPC systems and data centers. So that is the new computing continuum we have been talking. So then the question is, not only just where the data comes, how do you assemble, how do you learn things, but where to run these things, okay? So I need to do, let's say, continuous deep learning, okay? The example I gave earlier, like let's say in the digital field, I fly a drone, and drone is capturing the image, and then from those images, I quickly analyze based on my prior model, saying, oh, this part of the field has got disease X, this part of the field has got disease Y, then I spray appropriately, okay? So that is the kind of the new paradigm we are coming. I'm just giving one example, but you will see more examples here. So with this, let me introduce a very play a short video that actually motivates this problem.
A policymaker wants to know how land use policies will affect a region's biodiversity. A farmer is concerned about how new weather patterns will affect crop yield, while food distributors and public health officials are concerned with how supply chain disruptions will affect deliveries of nutritious foods to communities. Current technology can provide data and models to tackle grand challenges such as biodiversity, conservation, and agricultural and food system resilience. But it still lacks the infrastructure to link across data and models seamlessly to answer complex questions from diverse stakeholders' perspectives. Even AI experts are challenged to create standardized solutions across domains because a standardized cyber infrastructure integration with AI just doesn't exist. Enter ICICLE, Intelligent Cyber Infrastructure with Computational Learning in the Environment. ICICLE is an institute dedicated to building a national AI-driven computational infrastructure that functions as a utility, much like our electricity, water, and transportation infrastructure. This new utility will enable the delivery of AI to end users with the flick of a switch, enlightening solutions for imminent problems of national, regional, and local importance. ICICLE will provide an operational rationale and framework for a cyber infrastructure that delivers wide and easy access to smart computing, plus a conversational interface that allows stakeholders from diverse domains to ask questions and receive answers informed by currently available data and knowledge. For example, food distributors, emergency food agency managers, and logistics company executives might ask, which food supply chains will likely be affected by an approaching storm? The ICICLE conversation agent might respond with, I will predict future states of your regional supply chain under forecasted weather scenarios and evaluate alternative scenarios. Okay? Upon confirmation, ICICLE would then retrieve satellite data on weather, connect to weather forecast models, acquire inventory data for food producers, processors, distributors, transportation networks, wholesalers, and retailers throughout the region. Use AI models to forecast supply chain conditions from a baseline, and alternative logistics that maintain consistent food supply for vulnerable populations, and estimate supply chain disruptions based on historical and current data from other locations, mindful of privacy. ICICLE will go even further by accessing high-performance computing centers to backcast and learn how reconfigured landscape-scale precision agricultural production and distribution systems could integrate with alternative supply chain infrastructure to avoid similar future disruptions. Using an orchestra of smart cyber infrastructure elements, ICICLE produces a symphonic answer that improves outcomes for diverse stakeholders. ICICLE holds the potential to transform today's AI landscape from a series of fragmented tools for use by a few to one where democratized AI and integrated plug-and-play architecture empower diverse end users with knowledge and data flows that are science-based, traceable, transparent, reusable, and trustworthy. Introducing AI for CI for AI. AI for everyone.
So I hope that gives you a very broad perspective or a vision. So as you can see from the very top level, so this is like think of like a 2030, 2040. This is what we are aiming for. These days, if you see the example you saw, like the transportation, water, electricity, these days, like with the iPhone, how can we standardize the AI infrastructure? So in 20 years down the road, I mean, you don't need like these days, if you go to any HPC center or in a cloud provider, they have big pipeline. They're putting a lot of effort in putting all those components together and then give it to the users. But then you go from one cloud provider to other, the HPC center, every solution is different. Okay? So this is where we want to see how to standardize these. And our goal is to really have a plug and play AI architecture. Okay? Just imagine like you take your iPhone and plug it anywhere in the world, you expect it to work. If you are using WhatsApp, you want to see, I mean, anywhere in the world, if you just type, as long as you have an internet connectivity, it should work. So that's the kind of the goal we are trying to have, and then that will really democratize AI. So even a farmer can use AI without even knowing what is taking place. A shop manager can use the AI infrastructure. And of course, there are a lot of issues. There are foundational AI challenges, CI challenges. There are a lot of transparency, cyber security, all those issues also come in. And these are the actual societal problems. If you take a look at the digital agriculture, there is a societal problem all over the world. People have been trying to produce more and more for the increasing population, similar kind of thing, conservation, climate change, food insecurity. And while we are trying to do this, there is also a need to grow the next generation of workforce. If you see the AI field is evolving, but a lot of talents are not there. So next generation students and professionals need to be familiar with all these things. So this is the big picture. If you take a look, I introduced this emerging computing continuum at the bottom. Then we have the 3 use cases. So even in our team, we have actually people who are working with the farmers, who are working with the animal ecology, who are working with smart food set, the food distributors. So they are not computer science people, they are domain science people. But the goal is to really work with them. And this is our middle part where we are designing this kind of cyber infrastructure. I'll go into a little bit details. So the end goal is like, if you think the example we saw, like the shop manager is just trying to see, oh, hurricane or tornado is coming, what should I do? That's the only thing he or she will ask. And there is a big focus on conversational AI. So that he or she may not be knowing like a big programming, or you don't expect her to start running TensorFlow or PyTorch kind of thing. So this will be the conversational AI, but then behind the scene, everything else will happen in a transparent manner. So we have CI for AI. That is much more, all of you can relate to it. Like how do I really design high performance solutions, data management. I'll go into each one of these a little bit more detail. But there is a lot of interesting thing, AI for CI for AI. And this is what I think Arpan was asking yesterday. I answered, like, how do you, like, as these runs are happening, how do you really learn from them? Pure computer science, okay? If I'm running the same job 100 times and 100 times and at TAC versus Livermore versus HDSC, can I actually profile and then see what is the dependency between the underlying, might be the TAC, it is running on V100. at the SDSC, it is running on 800. Can I come up with a model? Can a model of those runs themselves? So that the next time a request comes, based on the availability, I can exactly determine where it should go. Because these are like urgent computing, I need to really solve it with a deterministic time. So then, of course, there is a lot of issues. Anytime we talk about AI solution, explainability, that is a big focus. That is also there. And then the privacy, accountability, data integrity, the software, and then co-design, and a lot of foundational systems AI challenges. So how do I create knowledge graphs? Where I put the models? How do I design model commons? How do I do adaptive AI? So those are the kind of the real research challenges. So we have this is a big thing. It's like there are 14 organizations here. I am the overall PI, but 14 universities. Here you can see, like starting from the East Coast, RPI, Delaware, OECU is the lead organization. OEC is also participating. Case Western, Wisconsin Madison, Iowa State, TAC, Utah, San Diego, SDSC, UC Davis, and IC Food. So these are the 14 organizations with 46 investigators, and we have around 50, 60 students. So it's actually a 100 members team are working on this. And of course, there are a lot of collaborators here, as you can see below. So these are the like that. So this big project has been divided into a lot of different thrusts. Just like I said, CI for AI, AI for CI, software architecture, analytics. But besides the technical issues, these kind of institutes, there is a lot of focus on generating like a workforce development. Okay, like how do you develop the next generation people, BPC, diversity, knowledge transfer, outreach communication, technology transfer, commercialization. So everything is built in because you are not just doing a very small project and writing 2 papers. NSF wants to see real translational impact, that at the end of the 5 years, people should be using this kind of a software and then really getting the benefits of this investment. And then we have that co-design. Those are our 3 leaders in those 3 areas. They are actually domain science people, and we have been working. We have a very excellent external advisory board. Some of you may be seeing, like Dan, he will be giving the keynote talk. He is actually on our external advisory board. Bipin Kumar. So it is not only HPC people are there, but the actual also the other from the AI domain, from the use-inspired science domain. So we have put together to get the real feedback from all of them. So this is how the technical things. So if you see this ICICLE logo, it goes from like a smaller size to the bigger size. So that is the idea, that it will be the unified software architecture which will be designed. But think of like a light version of ICICLE Lite is running on the edge device, right? With the ICICLE Medium is running on a medium scale server, and the whole ICICLE software stack is running on the HPC center. So they should be able to really communicate with each other with that intelligent computing continuum. So I'll just quickly highlight this just like a foundational systems AI. So here the idea is to really components which address the CI complexity and heterogeneity for plug and play. So we have, how do you create knowledge graphs? How do you establish model commons? How do you do adaptive AI, federated learning, conversational AI? So we have real AI people actually working on this aspect. So then we have the CI for AI. That relates to many people in this room. Cyber infrastructure for AI provides the necessary CI to deploy AI throughout the computing continuum, make it plug and play. So this is where high performance training, I think most of you are very much related to this. How do I really run the using a very large HPC systems? How do I do the training, machine learning or deep learning with the best possible time? But then it also goes into high performance data management. How do you design edge intelligence? We have actually some dedicated wireless team people also, because we are talking about democratizing AI and want to talk with the digital agriculture, the farmers. So if you go to that area, you don't get like the internet speed, what we get in this room. It is very low bandwidth. So how do you really make these things work? So it has to be adaptive, edge wireless. Then of course you need control and coordination. So then this is the AI for CI. Like using the AI itself, like we want to have the different kind of model commons for CI. We want to do intelligent modeling optimizations, applications, middleware, and systems. So everything will be put together. There is an existing software stack called TAPIS. Some of you might be aware of that. That is the Texas Advanced Computing Center. That project has been going on for some time, so we didn't want to start from scratch. So they already have a lot of these components, but then color-coded, the whites are already there, the light blue, dark blue, and then the orange. So these will be the components which will be added there. So in the end, it will be like a next version of the ICICLE, next version of the TAP is being transformed into ICICLE. So there is a lot of, I'll just take one example, just you see digital agriculture itself, there is a lot of cross coordination between all these different universities, the students, staffs from all the different thrusts. So if you take a look, just digital agriculture, we started this project in November 1st. So we've just finished 9 months. So it will be a 5 years project. But inside that, we are developing like an open source software for unmanned aerial vehicles, low latency inference as edge sites, high performance model training, model profiling, federated learning, and actually how to push these things to the end users. So just to motivate it, I'm just taking one example of this use case because of the limited time. But we are trying to do the same things for animal ecology and also smart food side. So as I motivated, I mean, there is a big focus on not just in US, all over the world. Any country you go, there is a lot of focus on digital agriculture these days because you want to have the harvest in the best possible manner with the lowest cost so that the food prices can be controlled. So here we have right-hand side, he's a computer scientist, Chris, but this Scott is actually from a food and agriculture faculty. Okay, so we are working. So as the examples I showed you, like let's say you fly a drone, can you exactly detect all these things, saying disease X, disease Y on a real time when you fly it? Okay, and then you can find out what exactly to be done there. Same thing is the water management. In these big fields, 200 acres, 2,000 acres, if you just uniformly treat the field, I mean, a lot of wastage will be there, and then the crop health will also be affected. So if you have a lot of sensors, in fact, the modern days, a lot of these devices are coming. We are working with an organization called CNH. So they have actually the real tractors. Tractors are equipped with Jetson, NVIDIA's, and all these devices. So you can actually get the data, do the inferencing, push the information to the tractors, and as the tractor is going, it actually takes the action appropriately. So we are trying to establish that complete loop kind of thing. And so as I said, like we just started this project, and in fact, just even these 9 months, we have got another like an additional funding from India. So they are also interested in the similar digital agriculture. So NSF from US and the Department of Science and Technology from India actually are collaborating to show that whatever we do there can be applied to India, or whatever they do there, can it be applied here? So that is a kind of a collaboration going on. So here is a very quick example. This is like my group mostly working on Arpan, Navaras. Here they actually worked on this project. So they are actually a definite model. Somebody has developed those model which can detect those diseases, but it was taking a lot of time. Here you can see like one epoch was taking 202 seconds. We reduced to 17 seconds. Okay, so using all the model parallelism, data parallelism, and all, whatever we do, the HPC people were able to reduce that. So we have given almost a 12x improvement. So that means I can do continuous training. As the new data comes, new fields, you should be able to achieve it faster and faster. And similar kind of things, this Professor Chris Stewart is working in that. So far, people, I gave like, let's say, one drone. But think of a very big field, 2,000 acres. If you just run even one drone, that's not good, because by the time the drone flies, it itself will be half an hour or 1 hour. So the question is, can you use parallel drones? Okay, so a lot of drones will be flying in parallel, and they will be actually coordinating. So there is a parallelism is happening now at the drones level. Okay, so they have developed a task parallel swarm. So I'll also play this video. You will see this is actually on the Ohio field. This has been done. You see these multiple drones. They take off, and then they are communicating with each other, trying to see, okay, I'll take this part of the picture, you take this part of the picture. They are exchanging with the servers, and in a coordination, they send the data to the end server, so where the training is taking place, and then the response is coming back. Okay, so that is the kind of the intelligent computing continuum. So this is actually an OSU student sitting in the farm, flying all those all those drones. So that is the kind of like the next generation kind of systems we want to design. So it is not just like you come up with a model, have the best performance, but really being applied to the field. So with this, I'll stop here. But this is again a big project. There is a big focus here on working in a collaborative manner with different universities, different industry, and really to make sure that we develop this kind of software and handle all the challenges, and which will be really be used, because this is a very NSF very special program. It is not just you write 10 papers. They are not happy with writing 10 papers. You write the 10 papers, but you convert those into the real translational aspect. Okay? So with this, I'll stop here. If you have any questions, I'll be happy to answer a few questions. Yes, Arpan, go ahead.
So I have a question on digital agriculture.
Yeah.
If a farmer wants to use this system, what prior knowledge does he need to have, and how much investment is needed from his side?
Okay, that is a very good question. Okay, so to answer the first thing, he doesn't need to know anything. Okay, that's what it is. That we want to democratize the AI. So the farmer doesn't need to know AI. He knows the agriculture aspect. We don't expect him or her to know about what is computer science, what is conversational AI. He or she will just talk to the iPhone or whatever the device. Okay. The next thing which, okay, so I think that is most important is how much investment he or she needs to put. Of course, that price has to come down. Okay, so this is, I am quoting Gilad, I had discussion with him. So he said AI as a service. So think of like, so this will get translated to like a monthly service. Okay, so if a farmer wants to actually use that feature, it might be $10 per month. I'm just quoting. I mean, at this time, it is not $10. It will be $10,000. Okay, but over the years, if it can be really democratized, and you bring the efficiency and reduce the cost, millions of farmers use this, then that will go to that kind of a $10. So just like currently we use internet, or you have a Netflix subscription, so it will be subscription based. And our goal is to really reduce that cost so that they actually see the benefit. If a farmer here is using, the next farmer is not using, there has to be a differential cost benefit, right? That will justify the overall.
Thank you.
Any other questions? So I think here several people. Can you raise hand? You people are working on the ICICLE project. I think Karen, Amir, Noras, Arpan. So like this. So a lot of just from our group, but within OSU, across all these universities. So it's a really big project. I spend now most of my headaches come from this, not from the MFH project. So, but this is a new kind of trajectory we are going, and I hope in the subsequent years we'll have very exciting results here. Let's see. Yes, Adam. Yeah, can you? Oh, sorry. Are you showing data sets? Yes. So that is a very important thing. So this is where that federated learning comes. Okay, I mean there are multiple things. Okay, so first is as we are developing this. Okay, let me start from the end user. So the question is, for a lot of these things to work, have the farmers, let's say digital agriculture, they have to share data, or we should have permission from them to really fly drones and get the data. Okay, and there are a lot of sensitivity there. I mean, every farmer doesn't want to share his or her data. So this is where the federated learning comes. If you know the background of the federated learning, you really don't need to have the full access to you don't need to know the data, but they can provide some APIs through which you can access the data while maintaining the privacy, security, those kind of things. Okay, so then we can actually build this model. Because for deep learning, as you know, if I just take like 5 samples, you cannot really build the model. If I have 5,000 samples, I'll be able to build very nice model. So that is what some of our colleagues, they know the farmers, so we are starting with them. The other thing is, as I said, like there are 100 people are working here. There's a lot of complex issues on IP. Intellectual property, 14 different universities are involved. Who will own the IP? Who will make money out of it? Those are the background things. This is where I get all the headaches, okay? So a lot of discussions are going on, but hopefully we'll converge on something. Because it is an NSF funded, we are mandated to share the data, we are mandated to share the results. So it is not a, we can't keep it totally closed at all. Yes.
So I might have missed it at some part, but at what level is edge computing, or could it be involved?
At what level? Which one?
At what level will or would edge computing?
Edge computing. No, there is a big focus here on the edge computing. If I go back, I mean, there is a lot of, we have dedicated people in the edge computing working here. So here you can see like a CI for AI. Okay, so there is a dedicated group for working on the edge intelligence. So let's say you are taking the sensors data, how much you keep, how much you throw, depending on the speed. Should I upload it now, or should I upload it in the evening, or where? So all those kind of things, you need to come up with uploading scheme, caching schemes, even to quality of service. So there is a lot of issues on the edge wireless here. Okay? We will not be designing new devices, that we are not planning, but using the existing devices, how do you make it work? So we are actually setting up an edge lab actually here at the OSU. Edge computing lab. So we'll have a series of different edge devices, so we can actually study all these trade-offs. Any other questions? Okay, so if not, I think we are just about the time. I think we have exceeded 2 minutes. So I hope this gives you a different perspective. I know there are a lot of different students. You don't need to always think that, oh, this is like the NPI. I'm just developing. Where it gets used, I mean, it has use at all different places. Okay, so let me then switch to the other the follow-up talks.